Okay, I guess we are about to start. We can roll the camera, but let's still take a bit of our time since we'll have people coming over. As usual, we recommend people following on Twitch. This is where it's going to be the best experience for it enables you to on Discord go into each your own rooms or channel and have a discussion there. So this way you can chat on top of the presenter without bothering him and work in teams. We've been doing that for the past couple of months, and I think this is the best experience you can get. At the same time, if you prefer to work solo, you can be on the live channel and watch Alex's stream right here from Discord. And as we did the past couple of months, we will have a game night after the event itself. We're gonna play. I'm gonna try sharing a Jackbox game, and we'll see what we want to play. But otherwise, we could play Secret Hitler or so on, or any member here who has a game to share. We can try as well. So without further ado, I guess I'm gonna introduce Alex. So Alex was kind enough to be our plan B for this month. We're working on having someone, and it didn't work out. So Alex is presenting more in a tutorial format than a CTF, and the only difference really is, I guess, it's because it was not a challenge of a CTF, but it was purposely made for Montreal, which is probably even better. So this is about heap exploitation, thus the meme heaps of fun. It's a rather difficult topic in the exploitation scene, but Alex gave us a rough tutorial before, and I believe he can deliver that in a very easy to understand and consume fashion. Still, this is 3 hour, so it might be a little intense. So I recommend people who struggle to ask questions, ask a text-based question in the various chat rooms. And also do not hesitate to come back to the stream and rewatch specific bits if you need. So I guess, Alex, I'll say thank you, Alex, and welcome.
Thanks.
So are you ready to go?
Absolutely.
All right, so the floor is yours.
All right, thanks, Olivier. So hi, everyone. Today I'm going to be presenting about the heap exploitation. There's 3 challenges, and before we go to the challenges, I want to go over a little bit of theory to help those of you who are not too familiar understand the concepts, and then you can get started with the challenges. Let me just get to my slides here. All right. For those of you who are only here for the challenges, you might want to take a screenshot of this right now. This is the information for the challenges. They should be up and running. Everything you need is on there. If for some reason it's not working, I'll try to be responsive, but while I'm presenting the theory, I might not be able to fix the server. So without any further ado, let's get started. The contents for today's workshop is basically I'm going to go over heap-related, heap-specific concepts, the bug classes that can occur on the heap, and kind of high-level / general method to attack heap. And then I'll go over a few hardening techniques to prevent those types of attacks. And after that, we'll get started with the challenges. And throughout the 3 hours tonight, I'll be dropping some hints for the challenges as time goes on. So, heap concepts. You've probably all heard about the stack, right? And there's this thing where should I put my data? Is it on the heap, on the stack? There's no right or wrong answer. But the stack and the heap serve a slightly different purpose, right? The stack is meant to store short-lived data, temporary data, stuff for intermediate computations and so on. And it's unique per thread. and it's volatile. So if you have data on the stack, but your function returns, that data is no longer in use and might change. So for that reason, you want to keep any data that lives longer or that needs to be shared with other threads or like other like state in your process. You want it to be on the heap. And then obviously the heap is actually it works with the allocator, which is basically an algorithm and some data structures that decide how the heap manages its memory. And we'll get into that in a little bit. But generally speaking, the heap is bad if you need a lot of allocations really fast. Of course, because it's I'll get into that in a bit, but heap has multiple allocation like algorithms, so some of them are designed to uh, like address those problems. Um, so like I said, allocators, there's like a malloc and free if you're doing C, new and delete if you've done C++, and maybe you know or maybe you don't, but new and delete for arrays is a different allocator as well in C++, which is why they always tell you to never like delete without the array index when you're deleting an array that you allocated with new. Normally, the allocator for the heap is managed by a common runtime library. So on Linux, that's libc. And like I said, you can have multiple allocators for like different use cases for what your program needs to do. Writing your own allocator is a little bit of an advanced topic, but it can be done. There's a few core so basically because you're tracking the memory, there's a few core concepts that you need to keep track of, and this metadata is basically to allow the heap to collect memory that's no longer being used and to decide how it's going to I guess place its data on in the allocated memory. So one of the things that you want is a free list where you keep track of all the allocations that were freed so that you can reuse that memory. And obviously, because you're tracking memory, you also need to track your allocation size so that you know how much space to free when somebody calls free. And some heaps support dynamic allocator changes. So hold on. Okay. So apparently we're having a bit of a trouble with the stream quality. If it gets too bad, I'll try to restart the video. I'm being told that it's all right now, so we'll just keep going. The allocator sometimes, if you have a like for dynamic heaps, sorry, my bad. For heaps, you can have a dynamic allocator that can be changed. Like normally, it's not during the runtime, but it's like at the beginning. You can like specify a custom allocator for debugging and stuff. So that's also something that your heap structure needs to keep track of. There's another thing that you need to be aware of for the heap. It's called the memory fragmentation, which is very similar to disk fragmentation. And it happens basically when you have small allocations that are freed and then they leave gaps in your memory. And these gaps are too small to be reused by any other allocation. So over time, you'll get a lot of fragmentation and you won't be able to do, even though there's like a lot of memory free, you won't be able to allocate big chunks of memory because the heap doesn't have enough contiguous space. So that's about that's a very quick overview of the the core concepts of the heap. Right now, I want to talk a bit about the bug classes that can occur on the heap. The first one is a buffer overflow, which you might be familiar with from like a stack exploitation, like a stack smashing and so on, which is the most common vulnerability. And it's basically when you do an unbound read, right? So you can see in my little image here, I'm going to try to highlight this. You can see, right? So this is an allocation. So this purple bit here is the metadata of the heap that I mentioned. So like the size of the allocation and so on. And this is an object here that was allocated, and it has a vulnerability, and it reads into a buffer on the heap, and you can overflow that buffer into this metadata and this other object here, and you're basically corrupting this data structure, right? So that can let you do some interesting stuff. Let me just get out of this view. The next one I want to talk about is the use after free, which is basically so this is the same heap as earlier, except this time we're freeing this object. So here the memory is freed and it's not in use, but
Alex,
yeah.
Do you mind restarting it?
Yeah, sure. I'll try that.
And it's weird because it's like barely okay, but for the recording, I think it'd be better if we take the few seconds to
All right, sure.
restart. Sorry, everyone. We had these issues before, so it should be fixed relatively quickly. But
This is better.
oh yeah, definitely. Thank you.
Okay. So use after free, right? You have this purple object here that gets freed, and now this memory is here unused, like this gray area here. And then you allocate a green object on top of it, but there's still this dangling pointer that thinks it's a purple object, right? So it's going to use that object as a purple object, and depending on what's there now, it might do something weird. Like in the worst case, it might not worse. In the nicest case, it might just crash, but in the worst case, it might read wrong data or data that you purposefully changed, right? And the last class of bugs that I want to talk about is uninitialized memory, which is a bit similar to use after free, but instead of being that way, is that once your purple object is freed, that data here is still there, and then I allocate a green object in this case, which has this uninitialized member, and you can see here that this is the leftover from the purple object, right? So you can imagine if I'm able to put an object there and force another object on top of it, which is going to read or use the data from my previous object, I can kind of control some values in the new object, in this green object here. So what that lets me do will really depend on what type of object is being allocated, right? So those are the three types of vulnerabilities. Now I want to go briefly into exploitation techniques. Mostly this is going to be like a brief kind of workflow that you can use to exploit or to attack a heap. It's sometimes it gets more complicated than that. Sometimes it's more straightforward than that, but this is the general idea. So the first thing to do is to identify a vulnerable object that's allocated on the heap. Like the heap itself is rarely vulnerable, like the allocator. What's going to be vulnerable is the objects that you put on the heap. So, like for example, if you have that yellow object from my buffer overflow slide, which reads some data and it writes it on the heap, but it doesn't check the bounds, so you can write past it and into the metadata of other objects. Once you have that object, you need to understand how the allocator works, and this is why where all the complexity of heap exploitation comes from. Is you will need to understand your heap allocator very well to abuse it. And what abuse means, I'll get to in the next few steps. But basically, that requires either code review, if you have the source code, which is going to be the case for the challenges tonight, or otherwise you have to reverse engineer it. So, like if you're doing heap exploitation on Windows, you don't have the source code for Windows, so you have to understand how their allocator works. So this is where the big complexity stems from. The next step, once you understand your allocator enough, is to identify some objects that you can use as a read and write primitive. And what the word primitive means is basically just a building block that you're going to use to let you achieve read and write wherever you want in the process. So we'll get, I don't want to spoil too much about the challenges, but this is something that you'll be doing tonight. And it'll make more sense once you start trying to attack the binary in the challenges. Once you have those primitives, the next step is to do what is called heap grooming, or also heap feng shui, which is basically because you understand the allocator, you're able to allocate and free different objects of different sizes until you're able to predict the layout of the heap. And once you're able to predict the layout of the heap, you'll be able to do, like in the attack, in the bug classes I showed earlier, you'll be able to know that the next object that you free is going to be in a certain position, and then the next object that you allocate is going to be on top of that freed object, right? So you control the memory where your object is going to be allocated. And this is crucial because that's how you're going to get those use after free or uninitialized data, right? And so then you use the bug that you identified to corrupt the heap, to corrupt the objects that you identified in steps 3 and 4 to get your arbitrary read and write primitive. And the next slide I have is going to discuss like what that looks like. And then after that, you might have to bypass ASLR by leaking some addresses or figuring out like where exactly you are. And then with your read-write primitive that you just created by corrupting the heap, you're able to like patch the PLT, for example, or like rewrite some code. It really depends on what kind of hardening the binary has. But from there on, you should be able to work your way to code execution and then get a flag, hopefully. So usually, arbitrary read-write primitives are very likely to be like kind of images, bitmaps, basically any object that has some metadata about a buffer, which, like for example, a width and height, and then a pointer to some data, right? Because if I'm able to say, for example, get a buffer overflow and overwrite the width and height of an image, then when I edit the pixels of that image, I'm actually writing to anywhere, right? So from the base pointer of data, I could make the width and height like FFFFFF, right? And that's a huge number. So now I can index data plus whatever, like 1 million, and edit the 1 millionth byte from data. So basically, you're bypassing the code that would check the bounds of that image normally. So that's the most common one. There are very creative ways to achieve that. Like if you have a primitive that decrements a byte by 1, you could technically use that to write anything, except you're going to have to write like 28 times to decrease by 28 until you get the value that you want, right? So heap grooming, I already mentioned. So you basically allocate free in it's a very heap specific way, right? So it'll depend on the heap allocator, on the algorithm, and like basically how the heap works, and you need to do it in a way that's going to let you predict the layout. So tonight the heap is very simple to help you predict the layout. So you're going to have to do a bit of code review, and then hopefully that's going to be enough. Otherwise, I'll be here to help you figure it out. Another technique, once you have this arbitrary read-write, right, is to craft a vtable. So vtable hijacking in C++, basically objects that use inheritance, they have this thing called a virtual function table where you store pointers to methods that can be overridden by subclasses. So if you're able to corrupt such an object and change the vtable address, then you can build a fake vtable, and whenever that object's instance has a method called on it that's in the vtable, it's going to go through your vtable and it's going to call whatever address you put. So that's a good way to control code execution. In non-object oriented scenarios, so like C, for example, instead of vtables, you're going to have usually objects that store raw function pointers, which is pretty much the equivalent. You just need to figure out how that function pointer is called. And that's pretty much it for the theory. Now I'm going to talk a bit very quickly about the hardening techniques. And then after that, we're going to go on with the challenges. So all of this stuff that I mentioned, right, the like use after free and uninitialized memory can be fixed very easily by having an allocator that zeroes out the memory. So if your memory is predictable and always set to 0 before like being given to a new object, there's no way that you're going to be able to have leftovers or to influence the values from another object that was there before you or that comes after you. After that, there's Heap Canneries, which is like exactly like stack canneries, which basically whenever the heap is doing its bookkeeping, so like to free memory or to like merge unused memory into one bigger block, if it notices that one of the bytes on the heap was changed, it can detect that there's an overflow and crash a process before something bad happens. Building up on heap canneries, and this is a technique that's usually used for debugging on Windows, guard pages. So you can put a guard page in between each allocation, and then it's going to be at the CPU level that you get a page fault, a page unmapped page exception that's going to crash your process at the CPU level. So it's not an in-process thing. The only downside to this is that you need one page per allocation to pad the allocation. And so like you're basically, if you allocate 5 bytes, you need to allocate a whole page, like so hex to 1000 bytes of memory. So you can see in like programs that use a lot of memory, this can get out of hand very quickly. Another thing is to randomize the allocator. So you try to make it so the allocations that the heap returns are not consecutive in memory, and not easy to determine. But obviously, if you're able to reverse the allocator, you can figure out a way to defeat that as well. So it's a limited mitigation, right? And the last one is encoding of metadata. So for example, you can XOR your allocation size or the next pointers with a key that's somewhere else in the heap to make it harder to successfully corrupt the heap. Because if I can corrupt the heap, but then any action that the heap has to perform causes a crash, then you're still protected, right? So that's kind of the idea of encoding that metadata that's on the heap. So that's all the content I had. I know I kind of rushed through it. The slides are going to be online as well. And the challenges are up right now if you want to try them. They're all in one binary. So this ctf.segfault.me on port 3000, you'll need the binary itself. You can get the source code. You can get the libc that you'll need for the third flag. And there's a template to get you started writing an exploit with Pwn tools. That's all on the website on the URL here. And I'll be going through the tables to answer your questions and see how everybody's doing. So have fun.
thinking this for too long. Send a message, you don't reply. I'll keep looking for you, even if it's wrong. I'm sitting all alone in my room. You're stuck so hard in my head. I don't care if there's no chance. I need to find you. I need to know. I need to know. I need to know. If I'm still in your heart. I called you tonight. I've been thinking this for too long. Send a message, you don't reply. I'll keep looking for you, even if it's wrong. Sitting all alone in my room. You're stuck so hard in my head. I don't care if there's no chance. I need to find you. I need to know. I need to know. I need to know if I'm still in your heart. If I'm still in your heart. I need to know if I'm still in your heart. I'll try stop the road to know if I'm still in your heart. I'll try beat up to find myself back in your heart. I'll try stop the road to know if I'm still in your heart. I'll try beat up to find myself back in your heart. If I'm still in your heart.
All right. So by now, I hope most of you are looking at the source code. We had a few issues getting it online. Let me just mute myself here. All right. So we had a few issues. The archive was empty. That should be fixed now. So you have three source files. There's ASCII.c, the heap.c, and heap.h. And I would suggest that you turn your attention to first get an idea of what the program is doing. So the program itself is ASCII.c, and then the heap code is the custom heap allocator. Before you try to understand the heap, which you'll eventually have to get to, but I would suggest to look at the ASCII program, understand what it does, and find a vulnerability. And this vulnerability, my first hint is this: it's somewhere in this create function. Oh, are we having technical issues? So somewhere in the create function of ASCII.c, you can find the vulnerable piece of code. And with that, you should be able to start looking into the heap and figuring out how to corrupt it to reach your goal.
Yeah, Alex, depending on where we were following you, like myself, I tried to stick on Twitch and I didn't follow anything. So you would have to start over. But if people followed you on the on Discord, I think it was okay.
Well, basically, I was just showing the code, but the only thing that really matters is that the vulnerability is in the create function in ASCII.c. So like, I think there was a bit of a misunderstanding, but that's really what matters here. So I just want to have some visual support. But yeah, I don't want to pinpoint where the vulnerability is. But I'm giving you the function it's in, and that should be enough to like understand what you're going to be doing, and then from there you're gonna have to look into how the heap works to do what it is that you're trying to do. I know this is very vague, right? But there will be more hints in a little bit. All right, good luck.
Looking for your face, fighting day by day. Anyway I look at it, I lose, 'cause I can't choose. Anyway I look at it, I lose you. Everywhere I'm looking for your face, fighting for it day by day. Looking for your face, fighting day by day. Looking for your face, fighting day by day. Speaking out loud, trying to make you proud, finding my place in your heart. Just tell me what you want to hear, since I'm feeling out with fear. Can't believe you're near, so let's stay right here. You're really making me see all of the good we can be here in your arms, counting all the stars. Oh, oh, oh. When will you have time to keep me in your life? So, oh, oh. Our past is forgotten, our stories rewritten. Seeing you smile, make it last for a while. Showing you my world and my heart. Just tell me what you want to hear, since I'm feeling out with fear. Can't believe you're near, so let's stay right here. You're really making me see all of the good we can be here in your arms, counting all the stars. Oh, oh, oh. When will you have time to keep me in your life? So, oh, oh. Our past is forgotten, our stories rewritten.
How's everyone doing here? Are you guys working on it?
Tonight, I wish that I had known. I've been sleeping alone, but you can't decide. And it is plain to see that your priorities just do not fit right. I can't reconcile this feeling. Whoa, whoa, 'cause I remember when you had certainty. There is empty space where your body won't lay next to mine. Nothing to embrace but the loneliness of this cold night. Oh, this fever comes and goes. Time slows. But the longer I belong, the more I grow. Trying to get over you, but you can't decide if you're still wanting me. And now this in between causes more divine. I can't reconcile this feeling, 'cause I remember when you had certainty. There is empty space where your body wants me next to mine. Nothing to embrace but the loneliness of this cold night. Oh, this fever comes and goes. Time slows.
So I'm going to give you the second hint for challenge 1. So by now you should have been looking at the create function in ASCII.c, and you should have figured out, let me just find it real quick. You should have figured out that this gets here, and then like most CTF, gets is always a big red flag on the title field of canvas is where your vulnerability is. So now if we look at the canvas structure, so if I go back to the top of the file where the canvas definition is, and let me just zoom on it. All right, so you can see, actually this is the, sorry, 1 second, a little bit higher here. So you can see here that there's this title pointer, and this is the first member of canvas T. And this has because of gets, it's not bounded, so you can basically overwrite. But if you go look at the canvas new function, you can see that the title is allocated on the heap to a buffer of 16 bytes. And this heap allocator is the custom allocator, right? So your idea is that if you overflow this title, you can modify other canvases that are on the heap right now. And now you should be looking at heap.c to understand the allocator. And I'll just give you a quick overview of how it works. It basically keeps, so let me just try to draw this. So the way it works is this is your heap chunk. And when you make an allocation, there's always going to be the alloc t that goes in the front of it, and then you have your data that goes here. And every allocation is going to be like that. So I'll just draw a few of them real quick, right? And what happens here is, so this is the canvas. This is the next one, which is the title. And then this is the next one, which is the data, the buffer for your canvas. And then here is the next canvas. So there's another canvas. So this is like, I'll call this C1. And then this is C2. And this keeps going forever. So for every allocation that you have. And if you overflow the title, I'll just use yellow again here, or I'll use red. If you overflow this, so this title buffer here, you can go and crush the canvases that come after you and this metadata. And going back to the actual code and the canvas structure, if I can get rid of my drawing. All right. Going back to the ASCII, you can see that there's a member private, which is 0. But this is obviously set to 1 for the first flag which you're trying to print. So your goal is to overflow and overwrite this private canvas, this private field for canvas 3, which is the one with the flag. Then if you can do that, after that, when you show the flag, it's not going to be restricted anymore. So that's challenge 1, and I'll give you until 8:30 to try and do that. After that, we'll go over the solution together.
Set it off, let your body feel the rhythm groove. Feet moving, your body turn into a wave. Let it go, you gotta let it go. Feel the rhythm moving through you. Oh na na la la, oh oh oh. Sending out that loving vibe. Oh na na la la, oh oh oh. Sending out that loving. You know you feel it, electric is in your body, babe. We come together to dance away all our inner pain. Hold me
So most of you by now have probably figured out what you're trying to do, and you're probably stuck at this point where you're not sure how to get in a state where you're going to be able to overwrite flag 1. So the first thing that I want to do is go quickly over the allocator so we can understand how it works. So we see this allocator here. If I go to the H file, the heap itself is basically a list of chunks, a function for freeing blocks, and a function for allocating blocks. And if you look at an allocation, it's basically it's a linked list of allocation, whether the allocation is free, the size of the allocation, and a back pointer to the chunk that the allocation belongs to. So this is because the heap allocator will allocate a small chunk, well, like a big chunk, but if you over allocate, it's going to allocate a new chunk and it's going to grow itself like that. So a chunk is basically has a pointer to the heap metadata, a list of allocations, and a pointer to the next chunk. So understanding this, we can look at how in the C file, how the allocator works. So by default, it's heap alloc here. When you create the new heap, the allocator is heap alloc. So I'm just going to go to heap alloc and look at it. And we can see that the first thing it does is it goes through the chunks. For each chunk, it looks for the first chunk that is not free and that has a size that is bigger or equal to what is needed. So this loop is basically skipping over all of them that are not free and too small. And then whenever this is done, if we have a free chunk, entry, then this free entry is good. Is big enough to handle the allocation. Otherwise, we go to the next chunk, and then there's like some logic that if no chunk has enough free space, we create a new chunk. But you can basically skip over this in most cases. So basically, what this tells us is that the if I have this heap here, and there's, let's say, a block here. Now I'm not gonna put the metadata, but there's a block here, and then there's another block here, and this block gets freed. The next allocation is going to go back here. It's not going to go here because this is the first free block that's big enough. As long, of course, as the new allocation is smaller or equal to this size, right? So it needs to fit in this block. And because in our current scenario, we have the heap, right? And there's flag 3 here. The flag is basically here. We need to overflow title from one of those chunks that comes before, so around here. So the way to do that is to delete any of those chunks and reallocate it. And then the new one is going to go here. And then when we overflow, we can overflow up onto the private field of the flag chunk, right? So to do that, now I'm gonna go into GDB to show you what this looks like. Actually, I already had running. So I'm just gonna start GDB with PwnDBG, and I'll zoom into this so it's readable. And I'll just start a challenge. Let me just move this a bit. All right. And I'm gonna set the breakpoint on show. And I'm just gonna run the binary until we get to show, and I'm gonna show the third chunk, which is the chunk which has the flag in it. And when I do that, I hit a breakpoint, and I'm inside of show, and I'm just gonna step one line so that canvas find runs, and that C has a value. So just hit next, and now I can do look at C. So it's a pointer to a canvas. If I do C title, it's flag 1, right? So I know I'm on the right chunk. And then what I can do is I can hex dump, and this is important here. This is something that a lot of people run into. You need to cast C to a byte-sized pointer, because if you increment pointers, it's going to increment by the size of the type. So by casting it to like bytes, I can increment by 1 byte or like 10 bytes, and it's going to be byte aligned. So when I do this, this is the raw bytes of my buffer, and we can see here, remembering the structure of a chunk. This is a pointer to title. This is what is this actually? Let me go back to the chunk struct. Here we go to this. So we go to the chunk. Is the width and the height and then it's private. So if I go back to GDB, we have the width, which is hex 25, which is 37, I believe. The height, which is 1, and whether it's private, which is 1 as well. So we need to overflow all of this and set a 0 here. And so to do that, you have to understand that title is read with gets, which while it overflows, it also sets the last byte to 0. So if we stop reading here, this byte is going to be set to 0. So that's pretty much what we're going to try to do with title. But now we need to find the buffer where we're going to. So actually, our plan is going to be to delete the canvas 2 with ID 2, which is the moose one, and then replace it with a canvas of like lesser size and start from the title and overflow all the way to here. So we need to find the title for the moose canvas. So I'm just going to do that. I'm going to go backward in memory. And so we can see here, these are the bytes for the moose ASCII art. And if I keep going, I think the actual offset is this. Yeah. So if I go back that much, I can see the beginning. So it's at this address here of the title of moose. And then all I have to do is take this address here and the address of this 01 here, which is this plus a little bit more, right? So if I do, let me just try this plus like 10. Is it 10? It's like, I guess it's 12. So that would be it, right? So it's this address here minus, which is this address here. And if I print this, I get this offset, 1558. So if I go back, and now I'm going to show you my exploit code to get this working. So there's all of this right up here. I'm going to skip all over it. I just basically, this is explaining what I just showed you. And you can see I set the size to 1558. And then I delete the second one. I create a new one. I make it 10 by 10. And then I print 1558 A's. And then I show the canvas. And this is going to have set the private byte to 0. So if I run this code now, if I zoom out to do this, sorry. I zoom out, I go back to my terminal. I close this and I run 1. And you can see I get the flag because I set the byte to 0, right? So that's it for challenge 1, and I'll give you a kickstart for challenge 2. If you open the binary in an editor, if you use readelf on it, you saw that there's a let me see if I can show this to you right now, or even just by looking at the source code, right? There's this thing flag2 here, which has a flag in it, and your goal is going to be to read that memory. So for this challenge, your goal is to find an arbitrary read primitive. Well, not find it, but build it using the same vulnerability that we just looked at. And if you notice, when I corrupted my canvas structure, right, I also corrupted width and height. So I want you to think about the implications of this. And if you need to, go back to the slides where I talk about the read-write primitives. And this should get you in the right direction. One last thing before I let you guys work on it, though. If you did checksec, you'll notice that this binary has address randomization enabled. So you will need to bypass ASLR as well. To do that, all you need to do is find a way to leak any address that you know is in the image. And then you can use, because you have the binary, right? You can check in the readelf or in Ghidra its relative address. And so with that, you can figure out where in memory your binary is located. That's all I'm going to say for now. I'm going to give you another hint in a little bit. All right, good luck.
I'm not looking for someone to dry all my tears. No, I'm not looking for someone to scare away the fears. No, I know it's not gonna happen. Don't believe in happy forever after. No one should have to feel this torn. We're unable to speak with voices to soar. We could do better than this. So devoted, I lost parts of me. This time it's not gonna happen. Don't need happy forever after. I let go of past if you do too. To leave now would be running from the truth. We could do better than this. We could do better than this. When you stand in the middle of the crowd, I wanna know it's me that you're missing. We could do better than this. We are much bigger than this. When you stand in the middle of the crowd, I wanna know it's me that you're missing. Me that you're missing. Me that you're missing. We could do better than this. Better. We could do better. Better.
so high, like we are not afraid to die. You're wild, oh then you smile and turn the sound up so loud, turn me around, round like a wolf. You have to learn. Oh, you brought me to life. I'm revived. I wait for you tonight. You're making me reach the sky.
right. So I'm going to give the last hint for challenge 2, and we'll basically stop at challenge 2 for tonight. We're running a little bit over on time, so I want to give you proper time to look at it, and I want to take time to explain the solution properly. And I'll drop a hint at the very end for challenge 3 for those of you that want to keep going. So the last, if you've gotten far here now, you know that you need to find this flag 2 thing, and I mentioned it a little bit earlier. You need to defeat ASLR, right? So there's some data on the heap structure that will be a pointer to any address in the challenge binary. And if you have that address, because you have the binary, you can use a nice little trick in, if I can find my terminal here. Right. You can use a nice little trick using readelf, where you can dump all of the symbols, and it's going to give you this thing called the relative virtual address of the symbol. So I'm just going to grep flag 2, and you can see this address here, hex 5020. That's the relative address relative to the base address of the image. So because of ASLR, the image is somewhere random in memory. But if I like draw this out here, so this is your image, right? And flag 2 is here. So I'm just going to call this F2, for example. And this thing here is the RVA. And this value never changes. Like the address here, this address might change. So this address might change, but this offset never does. This offset here never changes. So if you have this address, or if you have this address here, so let's say this is another function. If you have the RVA of this, you can do, I'm just going to type this, it's going to be easier, but you can do this RVA minus its offset, and the address that you have is going to be the base. So it's basically base is our VA minus RVA. And the VA is like the address that you would leak, for example, when you have a read. And then the RVA is whatever you find in the binary, in this case, 5020. And then whatever function you have the absolute address, you subtract the RVA, and then you add the RVA of flag 2 to the base that you obtain by using this formula, and you're going to be able to basically find any symbol in your binary. So that's how you're going to find the address of flag 2, despite there being ASLR in the binary. And that's the hint. And then like around 9:35-ish, we're gonna go over the solution in detail to how you can get flag 2. So good luck.
I'm terrified and loving it. Want no regrets to keep me up at night. Feel so alive and loving it. Had to survive, so I finally learned to fight. Laughter, we cry for the fun of it. Now I finally see the light. Don't wanna waste a single minute. Now I finally have you, got you by my side. Let's fuck it up and repeat mistakes. It's just a game we play. So let's hit the ground running. Yeah, let's hit the ground running. Yeah, let's hit the ground running. Yeah, so
was checking out pictures of us. I never realized what I have lost. Now I know it and it is so insane how I treated this like a game. You were my help when no one else were there to share affection. So let's try again. I'll go anywhere. Just send me your location to bring back when we were more than happy. Jokes and laughing, trust and loving, yeah. And we were storm and fire, both one body, more than happy, yeah. Yeah, oh yeah, oh anxiety, yeah, oh yeah, oh my many feelings inside, yeah, oh yeah, oh anxiety, yeah, oh yeah, oh my many feelings. I think we can rescue this. Just put the love first and taking the risk. Cause you're what I need and I'm what you need. You get my heart feel, you get my heart feel. Let's try again. Send me your location to bring back when we were more than happy. Jokes and laughing, trust and loving, yeah. And we were storm and fire, both one body, more than happy, yeah.
All right, everyone. I hope your brains are not too fried. We're gonna go over the solution for the second challenge. So like I said, we're not gonna go through the third one, but I'll drop a hint before we end the stream so that you can try it at home if you want. So for the second one, you needed to get an arbitrary read, right? And your goal is to make your way to flag 2 in the binary, which is right here. To do that, you had to corrupt a canvas, and as you could see in the first one, whenever you corrupted the canvas, you were also overriding the width and height. Let me just zoom this in. You were corrupting the width and height, which meant that when you showed the corrupted canvas, you were actually showing a lot of data. So that can be used to leak. The problem, though, is that when you're leaking that data, you're leaking data on the heap, which means there's like the addresses that you leak, if you leak any, are not usable directly. And what you're trying to do is to work your way up to any pointer that points to the challenge image, to the challenge binary, right? And to do that, we need to go back into heap.h and look at the structure of heap, right? So at the very beginning of the presentation, I mentioned that the heap allocator is prefixed for each allocation. Wait, let me draw this. So like you have the heap, right? And then you have this piece of metadata here, and then you have your actual buffer, like before, right? And this metadata has a pointer to a chunk. So I'm gonna try to write this. And then if we go back to look at the chunk, right? So you have a pointer like this to here, and then from the chunk, you have a pointer to the heap, so to here. So from here, you have this pointer to the heap. And this is where things get interesting, is from the heap, you have a pointer to the free or alloc function, so these guys here. So if you can work your way to these guys, you can have a pointer to the binary. And then from the binary, you're able to... hold on, I'm hearing that we have some performance issue on the screen, so let me just restart my stream. All right, hopefully this is better. Now I lost my drawing. Anyway, so you get a pointer to the allocator, and that's in memory of the image. So you can, because you have the binary, you can compute the RVA, which lets you compute the base address. And from there, because you know the RVA of flag 2, you can compute the absolute address of flag 2. So if you can overwrite any buffer and put its data pointer, so this pointer here for the ASCII, if I can overwrite this with the address of flag 2, then when I print the canvas, it's going to print this flag here. So how to do that? A lot of you probably thought about corrupting the buffer again, but then you realize you have to do multiple reads, and it becomes tricky because once you corrupted your buffer, the allocations are corrupt as well, and the canvases are corrupt as well. So as soon as you try to delete again, like everything's unstable and it's very difficult. And the idea here is to do a two-step corruption. So I'll draw my buffer again. So I have I'll skip the allocation structs, and I'll just go straight to the actual like canvases themselves. So you have canvas 1, canvas 2, and canvas 3. And the idea is that you use canvas 1 to corrupt only the width of canvas 2, which makes canvas 2's buffer point. So this becomes canvas 2's data, right? So this is C2 data. I can't write with my mouse. I'm so sorry about this. So that's C2 data, and you can index anywhere, right? And that lets you use edit, which edit, the function uses fget, so null bytes are allowed. So then you can completely modify canvas 3 at will, anywhere, right? So you can create the exact canvas 3 that you want. And this is super important because after that, you don't need to do any allocations anymore. You can just modify canvas 2 through edit, and then edit canvas 3. And then canvas 3 becomes your read-write primitive, right? So this guy this guy here is your read-write primitive. So this is very getting to be a messy drawing, right? But that's the main idea. And so once I have that, I'm able to leak the address of any chunk, and then use that address to leak the chunk. And then if I leak the chunk, I'm going to leak exactly. Let's see. So first, I leak the allocator chunk pointer. Then I leak the chunks. I leak the chunks heap pointer, and then I leak the free or alloc pointer. And then I do a little bit of math. I find a flag. I write the flag into the data of canvas 3, and then
I think you'll have to start your stream again.
Okay, I'll do this one last time. We're almost done, so after that I'll do the demo.
Yeah, but yeah, it was like worse than the other times.
Okay, how about this? Is this better?
Perfect.
All right. So once we have that, we can put the address of the flag in canvas 3, and then we show canvas 3 and we get the flag. So I'll go over the solution real quick. So these are the offsets that I grabbed using readelf, like the same technique I showed earlier for heap alloc and flag 2. And then, so this is all the write-up. I'll put those online after so you can read them. So I basically took the offset C1 size, which is the distance between the title of canvas 1 and the width field of canvas 2. And the reason is I'm only going to corrupt width and height, like I said. And you can see here this corrupt C2 function is actually overflowing canvas 1's title to be a bunch of A's, and then FF for the width and 1 for the height. Oops. So this is going to make the canvas 2 like a 65K by 1. And then after that, I can use canvas 2 here to read any address, any number of bytes by just modifying canvas 3's width and height and setting private to 0, setting the ID to 3 because it needs to stay 3, and then putting the address that I want to read into C3 data. There's one limitation is because of the way that the input works. It uses new lines, so you can't have new lines in your buffer. So basically, I just added a check here. If it's a new line, you just run again. Because of ASLR, it's likely that the second time won't have a new line in it. And then you can see edit 2 to repaint the buffer. And because the new line stops the read, I don't have to write 65,000 bytes. I can only write as many as I want. So when I get new data, I send the offset to get to the beginning of C3 of the canvas 3, and then I put exactly the payload that I built earlier to make C3 into the exact buffer that I want. Then I can show C3 to leak. So that's pretty much it for the arbitrary write. And then all I need to do is find the offset of the chunk, which is basically because we know that if I go back to this drawing again, oops, I'll do it red. So we know that the allocation, the metadata comes right before it, right? So I took this address here and I just do minus like whatever this number here is to get to the first parameter of alloc t, which is the chunk pointer. So this is what this does. And so basically after that, we only repeat using the arbitrary read primitive to read the chunk pointer. And then once we have the chunk pointer, we read the heap pointer. And then so these offsets here are based on the structures that are defined in the header files, right? And then finally, we get the heap allocation pointer. We remove the RVA, we get the base address of the challenge. Then we take the base address of the challenge, we add the flag 2 offset. That gives us the absolute address of flag. And then we read 37 bytes at flag, and then we get a flag. So let's see it in action, and hopefully it doesn't crash. Let me zoom into this. And then you get a flag, and so that's pretty much it for the second one. And lastly, before we go into the interview,
sorry to interrupt, Alex. Can you just like without drawing and showing source code, just basically like how exactly between what and what did you get the thing that allowed you to have your base address?
So at a very high level, I looked at the heap code, right, and it tells me like that the structure of a heap, each allocation metadata on the heap contains a pointer to the chunk, and the
The
chunk
next
contains
chunk.
the chunk that the allocation belongs to. And then it doesn't really matter which chunk it's pointing to, but what matters is that the chunk has a pointer to the heap, and the heap itself has a pointer to its allocator, right?
Okay, so once you have these, then you can figure out this delta enables you to figure out basically by removing one another and knowing the size of the structure that is allocated, you can get back to the base, because these are not
Yeah,
relative addresses but full on addresses.
Yes, because I have the binary, of course, which is why the binary is provided. So I have the offset relative to the beginning of the binary, and that lets me compute the base address of the binary. So that defeats ASLR completely. And then because I still have the binary, I can compute I have the relative address of flag2. So from the base address, I can compute the absolute address in memory of flag2. Is that clear?
One last time, but slower.
All right. So again, on the heap, whenever you make an allocation, right? This heap in particular, like I'm not saying this is how it works for glibc because each allocator is different. But on this case, this heap has a alloc t in front of every allocation. This alloc t, so I'll go back to the code, has a pointer to the chunk of the memory chunk to which the allocation belongs to. So then I follow this pointer, I look at the chunk. The chunk has a pointer to the heap that it belongs to. And then I follow this pointer and I get to the heap itself, which has a pointer to its free function and its alloc function. And these are the two pointers that I was talking about at the very beginning in my slide, where I said you can like modify these to like get basically to point to other code, right? So in this case, I don't want to modify them. I just want to use them to defeat ASLR because I have the binary locally, and I know that the binary itself will move randomly in memory, but the binary, like what's inside the binary, doesn't move. It stays relatively in the same location. So I'm able to use that fact to, if I have any pointer to the memory of that binary, to find its base address in memory, regardless of where ASLR decided to put it. And from there, from the base address, I can compute the absolute address of any symbol in that binary because I know because I have the binary itself on my disk, and I can compute or look up rather the offset for any symbol and then add it to the base address, right?
And how do you leak the address, this address?
By corrupting the any chunk to have a big size, and then
A
taking
chunk is not the same as a canvas. A canvas is
sorry,
inside a chunk.
sorry. I meant a canvas. Yeah, by
Okay.
corrupting a canvas's size, so that when I show it, it's gonna leak a lot of memory, right? It's gonna leak like whatever 6,000, like 65,000 bytes after it. So in those 65,000 bytes, if there's an alloc t, I can get its address, right?
Yeah,
It has to come
and then
after.
boom, you got it. Okay,
Yeah.
I understood. Oof.
All right. So I'm gonna drop one hint for challenge 3, but we're not gonna do it because we're out of time. Now you have arbitrary read, right? The next step is to get arbitrary write, and you're not that far off. But then the final step, once you have arbitrary write, is to get remote code exec, and that's the last challenge. So it might end up on Ring 0, or it might I might post a write up of it at some point. But I hope you had fun. I hope you learned something, and stay on. We're gonna do an interview in a few minutes. And thanks for coming.
Yeah, I don't think it's gonna take a few minutes. Just about setting up the camera,
Sure.
because we're streamers now. was very good, but oh my god, I don't know. I'm not made for this.
All right, so I guess I can stop sharing my screen now.
Yeah, your screen is no longer on.
All right, good.
But I think this leads nicely into the first question.
Yeah, sure.
How did you get started in binary stuff like exploitation, reverse engineering, low level?
Well, I mean, when I first started my career, I was a software developer, right? So I spent a lot of time like coding and also debugging code. And like there was this point where I think most people like kind of gave up was when the bug was so deep that you kind of had to start looking at assembly or understand like very low level stuff. But for me, that was the point where I realized I really loved this, right? And then I just like wanted to learn more, so I started like reading about assembly. I started like reading about low level stuff, OS internals, and that kind of thing. And there's no really like precise point where I realized like, hey, I'm good at this. It was just like it came over a very long period of time where like before I knew it, I was like very comfortable looking at it. And also like for reverse engineering, it started as me trying to reverse some like video games that I played, and like part of it was to like defeat like their anti-cheat system because I wanted to create a custom client to connect to the server directly, and that was like my first really big reverse engineering project, and that's when I realized that there's all this stuff about like obfuscation and like DRM if you want, like code like code virtualization and so on, and that really took me down a huge rabbit hole that I think contributed to a lot of what I know now because I had to look this up and like learn it the hard way.
And like you can't learn that stuff alone. You need some like website or reference or forum of some sort, right?
Yes and no. I think like obviously it's gonna go a lot faster if you have people to mentor you and like other people to like bounce ideas off of. But I can tell you for a fact that just spending time like looking at what it's doing and like thinking about it, and like obviously the OS internals you have to read about it. Like nobody is gonna go and like figure out how all of like Windows works, for example, without reading any book about it. But the actual like reversing and getting the intuition for it, I think it's like a lot of doing it by yourself. Like when I started doing it, I had no clue. Like I had basically the x86 manual open next to me, and I was like looking at instructions like every like 10 seconds. Like you read one line of assembly, you're like, what does this do? And then you read the next one, what does this do? And then after like a long amount of time, you start to like remember those things and like be more efficient with them.
But still, you need to level up at some point. You can't like open, let's say, a Discord Windows executable and start looking at this without knowing if it's packed or not. Like there's isn't there an starting point?
There's a question in chat. Hold on.
Yeah, no, I'll get to it. I saw
okay,
it.
my bad.
I
All
just want to finish with this
Okay.
thread and
Yeah, sure. So yeah, I mean, to be completely transparent, the first binary that I reversed, like as in not debugging but actually reversing, I had no idea it was packed. I was just like, I started at entry point and I was reading, and none of it made sense to me, right? Like, I mean, I didn't know what a real main function looks like. I didn't know what obfuscation looks like. I didn't know what, like a packer looks like. So I was just reading it and just trying to understand it. And then I was like, wait, it looks like it's like iterating over some blob of data or whatever, and like trying to look at what the data is, and like, it looks like this data is like trash, it's junk, or it's encrypted, or it's like compressed or whatever. And then I just like looked up like papers, like read online, just do like what the hell am I looking at, right? And after a while, it's sort of like, for instance, I was looking at this tidbit of code that was like resolving imports through like hashes, right? So hashing a symbol name and then looking it up. And it took me like maybe like 3 months to figure out what it was doing because I didn't know what I was looking at. And like even if like I couldn't just look it up. You're looking at it, you don't know what you're looking at, you don't know what to look up, right? And so now I have a bit more clarity and like I understand how it works a lot more. So yes, I can look it up, right? But this initial step where you don't know what you don't know is like I think I'm sure if you have someone that teaches you that, you get over it a lot faster. But for me, it was a kind of self-taught process.
I just googled perseverant in English because I wasn't sure what it is, but I mean this describes you pretty well. It's like persevering, like
Yeah,
you didn't give up. Because I mean 3 months looking at the pack binary, I wouldn't know many people who would go through something like that. It's not rewarding enough, right? It's
yeah. I don't know if it's perseverance or if it's more like headstrong.
stubbornness.
Like, yeah. I think it's just like once I make up my mind, like this is what I want to do, is just I'm never gonna stop, right? And
Well,
so
I mean,
that's more like it.
yeah. There's a question in the chat room. How old were you when you started your career in cybersecurity?
So I don't think my career in cybersecurity is very representative, but I guess I was 28. I started in 2018. So until 2018, I was a software developer full time, working in and like C++ and like very low level stuff. So I think that really helped me kickstart my infosec career, I guess, because it came with a lot of background like IT stuff and also development stuff, and like I had a very good like web background, I guess, from like developing web apps and stuff. So I would say like unofficially, it probably started from the day I started being a software developer, but I actually only got interested in cybersecurity because of reverse engineering, and that really started off like in the like around 2015, and then slowly worked my way up to actually making the switch in 2018.
And in 2015, instantly you connected with the cybersecurity community in Montreal. That's how it happened, right?
In 2018, actually. Before that, I was interested. Like I had an offer to work as in a cybersecurity team, like a AppSec team, but I like because of reasons I couldn't take that offer. So it actually started like I started considering it in 2017, and then a year went by, and then I was kind of getting tired of the projects I was working on, so I wanted a new challenge. I decided why not try it, you know. And then my expectations was to do a lot of reverse, but it turned out that's not what I did. So I ended up finding about Go Secure through Montreal, actually, um, uh, and then going to the cybersecurity route through there in 2018.
Yeah, I was messing with you a little bit with my last question because I remember that when you first came to Montreal, you didn't know about uh, Montreal or NordSec or even Hackfest. I think I was kind of surprised
So
because
I learned,
we
yeah. Sorry, I learned about all of this stuff basically 2 years ago, which was when I first met you at Montreal.
and at the time where we were drinking in person, the good old
Yeah,
days.
yeah, prior
But
to COVID.
I think we adapt fairly well, and we're geeks, so staying at home is our cup of tea. Um, but Nitbix asked me to, or ask the chat to talk about radio challenges. So, does your how does reverse engineering help you regarding those, and what do you have to say about radio challenges, or I guess it's ham radio or something like that?
It has nothing to do with my reverse engineering background. It's I think an inside joke, mostly because there's a challenge on Ring Zero called the SIG ID2, which I spent literally like 4 months straight like raging and like literally raging about it every single day, and like my life for that moment was just pure SDR. I was taking like a master's class on like radio signal processing on YouTube, trying to figure out what the hell I was missing to get the flag for that challenge. Um, and
I
so
thought
I
you
think
were
that's
gonna say pure hatred, but you
no,
said
no, no,
pure
no.
is SDR, which is better, right?
Yeah.
But so did you solve it?
Yeah, I ended up solving it, and then after that, I was like, I'll never do SDR again in my life. And then Hackfest last year had SDR challenges, and of course, I was the one that had to do them in the team. But yeah,
Because you had the most experience.
yeah, exactly.
All right, another question from the chat. Do you have any advice on getting an entry-level internship or job in cybersecurity?
Um,
It's from
I-
Pone Alone, by the way, and thank you for your questions.
Yeah, I'd say get involved with the community. That's definitely a really good way. Like talk to people, like do CTFs, and really just like be passionate about what you do and like show that you're passionate, and that goes a really long way. Um, I can't really comment about the specifics of getting an internship in cybersecurity because I just did the switch from software development, right? So but definitely like uh being invested in it and showing that you care about it is a good way to show people you're interested.
Yeah, if I may add also, like I'm looking for interns 3 times a year, and the thing is, I don't know how other companies do it. They probably do it through their own internship programs. But the thing is, there's a lot of interest around these internships, and the skill set required is quite high because we have the chance of having a great talent pool out here in Montreal. So it's kind of difficult to get your first one, I think, and this is why Alex's comment is very on point. It's because if you have a profile on Ring Zero, if people know you, not only you'll be you have more chances, but you'll be the one to know about the open position first. Let me give you a very specific example. When I look for an intern, if it's not already fulfilled by word to mouth, bouche à oreille, you know what
Word
I
of
mean?
mouth, yeah.
Word of mouth, exactly. I knew I was wrong, but I knew I was far. If it's not already fulfilled by that, then I post on, like, for example, the DCI Slack, so the Slack of ETS University, and then it won't take long before we fill the position. I think Montreal, we there were some emails back then. There might be also other times where we will communicate on Slack or Discord about stuff like that. But lately, we've been just doing it by word of mouth,
Yeah.
word of mouth. So, but it's difficult, and we're trying to give a chance to everyone. Our current intern right now is in my research group. It's a long shot guy that moved to Montreal for his internship, and he's been scaling, like learning a lot like crazy. So it's not true that we only take experienced people, but it's a matter of luck because we take one, right? So imagine if all companies only have one intern for pen test or hands-on roles. It's difficult. And for other, let's say, other parts of cybersecurity, for example, managing firewalls. You cannot put an intern to manage firewalls because firewall is production. Production can't break, and uh, like it might happen, but it will be very rare cases, and it will be cases where everyone will double check the changes, and this is not a pace that an SME can afford. And if it's in a big company, I'm not even sure you want to manage firewalls for a big company. So it's a difficult question, Pone alone, but uh, being close to Twitter or cybersecurity communities will definitely help. Eric asked earlier if you would make the solutions available, but you already said you would,
Yeah.
Alex, right?
Yeah, it's all gonna be on the Montreal GitHub. I'm gonna upload the solutions, the slides, pretty much everything that was made available today, and pretty much everything I have about those challenges. So yeah.
So I don't know. I'm inspired, but I know you're a fit person, and you do biking and you run.
Yeah.
But let's take the to be fit, you need to train every so often, right? You cannot bike 1 time a month and be proficient at biking, right? You will
Right.
lose your endurance or whatnot. Do you think the same thing applies to like RUP gadget or heap exploitation, like the low level binary? We can always remember an XSS as the simple ones at least, but is such a thing as barrier to entry, or as a minimum training amount of hour per month to do low-level challenges?
I think it applies to everything in general. Like, if you, and this is especially from back when I was a software dev, right? Is if you go away from a stack from any amount of time, when you come back to it, you're rusty, and like you might need to open up the documentation more often. You might need to Google stuff more often because if you're not using it frequently, your brain kind of puts it on the back burner, and like you'll have to actively go back to that knowledge to refresh it. So definitely, and especially for like very complicated stuff and low level stuff, you need to. The more often you do it, and the more you're involved in it, the more fresh it stays in your brain, right? And so you're gonna have that knowledge on hand more easily. And if you stop for like months or years, when you come back to it, like you're not gonna lose it, right? It's like biking; you're not gonna forget how to do it, but you're gonna have a bit of ramp up to get back to where you're comfortable, right? So to keep going with your parallel of physical training, it's like you don't just like stop running for a year and then like get up and run a marathon, right? You're gonna hurt yourself, and it's the kind of same thing with anything in the software world, I think.
But okay, but so like learning the ins and outs of Python, you don't think it's more like running a 5K, and doing Heap exploitation is more like running a marathon, and so you need to your minimum amount of running per month varies based on what you're trying to do?
Well, yeah, it will certainly like you'll have to have that knowledge more ready on hand, but like you'll need a ramp up period. But I mean, it's not like I wasn't really doing heap exploitation in my day to day until I had to make those challenges, right? And I just went off of my general knowledge. I like to be fully transparent. I had to look up a lot of stuff as well when I made the challenges. I had to test them. I had to debug them to make sure that they work. And I even like found some stuff that like I had to change because when I tried to exploit them, I realized that it wouldn't work because of this or that reason, right? So yeah, there's definitely a ramp up, and
Even the way the structure is laid out, if you did something else with it, it would prevent exploitation, for
yeah,
example.
yeah. Like for example, if the next in the chunk, the canvas structure, if the next pointer was first, as soon as you would overflow it, you wouldn't be able to traverse the list anymore, so it would crash. That's one example.
All right. But I mean, you've been very generous. I think we spoken enough. Do you have anything you would like to say as a last word? Do you need like are you building a team for NordSec for next year, or you have something to share to our audience?
Nothing specific. I'd like to say, well, thanks for having me, and thanks for attending, and like, hopefully you had fun with the challenges. And I really like hearing the feedback when I see people actively trying them and struggling, or just that like that spark of when you finally figure out what it is. And like, I mean, that's why I do this, right? That's why I love designing. That's why I love presenting and teaching stuff to people, is to see people understand, get it, or like crave more, So, well, thanks to Montreal Hack and you and like everybody involved for making this possible.
Well, thank you so much, and for your time and the last minute cover up. It was very appreciated, and these tutorials are landmark, right? We're gonna get back to it because they're well explained, and they have a long lasting value. So thank you again so much, Alex.
Thanks.
So we're gonna migrate onto the games. We might have a couple of glitches because I know that our usual provider of gaming are gonna be are not here, so I need to manage it basically, and I haven't done that in a while, so we'll see how it goes. But it might be possible it will work just fine. I think we do this on Benelux Virtual, so the we'll probably cut the Twitch once I before I started struggling with my English, and then so we can all move away there. I'll start a game, and we can also figure out if we want to play more Secret Hitler or Jackbox TV. I have a license of I don't know which one, but I do have it. So let's just get started. So thanks for everyone, and see ya next month or in 5 minutes.
Bye bye.
Bye.